This is problem 6-128. It's on page 326. Determine the forces which the pins at A and B exert on the two-member frame which supports the 100 kilogram frame. Okay. So the frame looks something like this. We've got a pivot support at A, and then a pin at C with a member that moves down to another pivot support at B. Then there is a pulley that is centered at C, and then a rope attaches from the center, from that point C, wraps around another pulley and goes back up onto the pulley, and then there's tension in that rope so that we can support a weight. Now this weight is 100 kilograms times 9.81 meters per second squared, and so the weight is 981 newtons of force. Now there's some relevant geometrical information given. Let me copy that down from the figure. The height here between B and C is 0.4 meters. The width between B and C is 0.6 meters. So again, a 4, well, is that a 4, 5? No, it's not. Yeah, it is. It's a 2, 3, 5 or a 4, 6, 10. So the length of this side, squared is sum of the squares. You can figure that out. I'll write it down in a minute if we need it. 0.8 meters on this side, horizontal distance between A and C, and 0.6 meters height difference between points A and C. Now point D is down here, and I think that's all of the information that they provided. Now I went ahead and calculated the length of the sides, just Pythagorean's theorem. A to C is 1 meter long, and C to B is root 0.52 meters. Okay, so there's our relevant geometry information. We're supposed to find the force in AC and the force in CB. Apparently we're sizing these supporting legs to make sure that they do not fail. So let's begin with a free body diagram of the weight itself so we can kind of figure out what's going on there. The weight, of course, acts downward on the object, and the pulley pulls upward. So I'm going to take the pulley and the weight as a free body and write that the rope has tension T supporting the weight. And from this free body diagram, it's pretty obvious the tension is half the weight. Okay, so that would be a total of 490.5 newtons of tension in the rope. Now if we consider a free body diagram of the pulley at C itself, let's see, let me draw it over here so it makes sense. We'd have tension acting down this way. We'd have tension acting this way. Now remember, this is just the pulley itself, right? We're not talking about point C. Point C has other things going on in it because of the supporting members. We're not talking about the pin at point C. I'm talking about just the pulley. For the pulley to be in static equilibrium, there must be a force up and to the right on it. In fact, the magnitude of those two forces would simply have to be T. Because look, we've got tension pulling down, so we have to have that equal and opposite force up, similar to the similarly in the horizontal direction. And of course that body would be in static equilibrium because the moment of the horizontal couple would balance the moment of the vertical couple. Okay. All right. So what about the frame then? What about if we take the frame itself? And I guess I'll put all my free body diagrams on this side. So if we look at the frame itself, we know that A, C, and BC are two force members. Therefore, there must be a load in each one acting along the members themselves. What else acts on this frame? Well, there is a tension T that acts from the rope connected, and because the pulley is the only other thing connected here, there must be equal and opposite tensions, or tension magnitude forces acting at that point. All I've done is I've taken these two forces from the pulley, reversed them, and applied them to the frame, because they have to be equal and opposite. Okay? So understand, this tension magnitude force comes from the pulley. This tension force comes from the actual tension in the rope. Okay, so what if we were to sum forces in the horizontal direction? Well, we'd have ACX minus CBX, so the horizontal components of those two forces at the base minus the tension equals 0. And so AC, let's see, to get the horizontal component, what would I have to do? Well, I'd need 0.8 over 1, because I would need to, well, hopefully you see that there's a triangle in here, right? So its base is 0.8 meters, its hypotenuse is 1 meter long. That would be ACX, and then put everything on the other side. So I'd get, well, or better yet, let's keep CB on this side. So minus CB, but I need the X component of CB. Well, there's another triangle right over here. See it? And that triangle has a base of 0.6 meters and a hypotenuse of root 0.52 meters. Now let's take the tension and put it on the opposite side of the equation. And I'm going to call this equation 1. Now it doesn't help me a whole lot, because while I know the magnitude of the tension, I don't know AC or CB. So this is one equation and two unknowns. Where could I get another equation? Well, what about if we try summing forces in the vertical direction on this frame? Well, let's see. We'd have ACY, the Y component of that, plus CBY, okay, the two support reaction forces. And there are two magnitude tension forces acting down. So what we'll do is just go ahead and move those two tension forces to the right-hand side of the equation. And you know what, actually, I've got enough space. I was afraid I was running out of space. We'll leave it there so it's clear. And then AC in the Y direction, well, it acts along this hypotenuse, so it would be 0.6 over 1. To scale AC, the total magnitude, to get the Y component, plus CB, we need the Y component there, 0.4 over the hypotenuse, root 0.52. Okay, and now we'll put the 2t on the other side. So what do we have? Well, we have two equations, two unknowns, right? Equation 1 is here, equation 2 is here. And what I'm going to do in order to solve those is to rearrange them just a bit. I guess we don't need the free body diagram anymore. I don't want to forget that the tension is that much, but we don't need any of these free body diagrams. I just need that equation. What I'm going to do is rearrange these two equations just a bit in order to solve, or to make the factor on AC equal to 1. In other words, I'm going to divide through this whole equation by 0.8. So I will write AC times 0.8 divided by 0.8 will just be 1, minus CB times 0.6 over 0.8 root 0.52. See what I'm doing there? I'm just dividing through by 0.8. On the right-hand side, then I'll end up with T over 0.8. Okay? The 0.8 over 0.8 canceled with the AC term. Let's do something similar for the second equation and write AC minus, well, actually plus CB times 0.4 over 0.6 root 0.52 equals, so you see what I'm doing is dividing by 0.6 in both cases. So I've got to divide the right-hand side by 0.6. So it equals 2t over 0.6. The reason for doing that is because I can simply subtract one from the other. So if I were to subtract this whole equation from that equation, that allows me to solve for, well, that allows me to eliminate AC, because the sum of those two will be just 0. And then we'll have minus CB 0.6 over 0.8 root 0.52. And we'll have minus, because minus of plus is minus, so CB 0.4 over 0.6 root 0.52. On the right-hand side, we'll have t over 0.8, but then I'm making all of this negative and adding, so minus 2t over 0.6. And there's our equation that has only the tension and CB in it. If I factor out CB, then what we'll have is negative 0.6 over 0.8 root 0.52. I guess I could have pulled out the root 0.52. Minus 0.4 over 0.6 root 0.52 equals t, and we'll do the same thing over here, pull out the t, 1 over 0.8 minus 2 over 0.6. And hopefully you see that what we can do is calculate the magnitude of these terms and just solve for CB. So for example, the magnitude of this whole term, this mess, comes out to, well, let me put it down here, comes out to negative 1.964563. This term on t came out to negative 2.083 repeating. And so hopefully you see that we just take tension times negative 2.083 divided by negative 1.96. Notice that negative 1.96 is close to negative 2, so is negative 2.083. So we expect to get about 1 for the factor on t, so we expect CB to be just slightly larger than t, because we'll have something bigger than 2 over something smaller than 2. So CB, in fact, comes out from this to be about 520.15 newtons. And that makes sense because the tension itself is 490.5. So we got something, as expected from the math, just a little bit larger. So that tells us the force in member CB. Let's write it down over here. So 520.15 newtons or so, close enough for our purposes. And then the last thing to do is to calculate AC. So what I chose to do is just take this equation, rearrange it a bit, and write T over 0.8 plus CB 0.6 over 0.8 root 0.52. And of course we have T and we have CB, so we can plug in the numbers and find the force in AC. I'm going to just write it down over here. When you calculate this out by plugging in the proper value for T, what, 490.5 or so, and you plug in CB, the 520.15, what you find is that this is about 1154.18 newtons. So that tells us the force in both of those members as well as the tension in the rope. And notice we didn't really have to break up A, B, and CB into vertical and horizontal components. In fact, if you sum forces on the overall machine, AX, BX, for example, you'll find that the horizontal components of A and B cancel the tension T. And you can use that as a check if you like, but there's the solution to the problem.